afternoon. Today's webinar fits within this larger webinar in two sessions called Crossed Views on the AI Applied to Water Sciences. First part was called Talk, listening to students, took place on Wednesday. So there were sources and PhD students who talked about the way they use AI in water sciences, the work they carried out and using this technology, and they could talk about their questions and interrogations about AI and how they see the use of such tools in the future. So in the near future, you will be able soon you will be able to see this webinar again on H2O website or on YouTube. This afternoon, this is the second session of this webinar from theory to practice, and it takes place from 2 to 3:30 and not 4:30. And this webinar we will listen researchers and engineers who work in water domains, and they will give you concrete examples of the use of AI within the framework of their projects. Three speakers today. First will be Mr. Nicolas Baghdadi, the research manager at the INRAE, the National Institute for Research for Agriculture and Environment. He works also with the Tetis laboratory. Then Mr. Baghdadi, you worked at the BRGM in Orléans. BRGM is the national, it's the Mine and Geological Research Office, and you talk about teledetection for soil moisture detection and the mapping of irrigated areas and the assessment of biomass. Then we'll listen to Pierre Lemaire, who is a research engineer specialized in computer vision and machine learning, and today he works with the STIX 4D, this engineering office. He works in geomorphology. You did PhD at the Information System and Imaging for the recognition of facial expressions, and you work postdoc on the utilization of drone and for the images in Lyon laboratory. Last speaker will be Mrs. Emma Schymanski, professor in environmental cheminformatics at the University of Luxembourg. You are also deputy director of the LCB, the Luxembourg Center for System Biomedicine, and you're a member of Open Science and Research in Data Management, so both in Luxembourg. And you will discuss your research on exploring water combination with open chemoinformatic approaches and open source data. Perfectly, thank you. Of course, the speakers do not cover the entire diversity of application of AI in water sciences. There are many, many other topics and utilizations, and today we'll give you a kind of an overview of a couple of topics. Prior to kicking off this webinar, and just to give you more of a context, webinars are organized by the students of the interdisciplinary master integrated water sciences from the H2O Lyon Research School. And this year within the framework, and I belong to this, and Louis too, and within the framework of a teaching unit presided by Mr. Cherki in Lyon, we worked on the utilization of AI in water domains or water science, and we did four research on four different topics. That is detection, prevention of leakage in drinking water networks, tracing of pollutants, remote sensing and thermal detection. And thanks to all this knowledge for another teaching unit run by Antoine Vernet from the Lena Lab, part of our group work wrote a vulgarization article with high school students in Lyon it was published in a Decodé journal, which is a vulgarization journal for high school students. And the work that use generative AI were also produced by some of our students. And the work were presented during the first webinar, which should be available on the internet soon. And the organization of the webinar comes in addition to all the works to disseminate the knowledge we gained, works we've done, as well as this, to introduce other participants who use AI in their work and to share with them the utilization and the feedback of such utilization. With no further ado, we move on to Nicolas Baghdadi for his presentation. Good afternoon. So I'll discuss satellite images contribution to assess moisture of soil in agricultural area. And I'm Nicolas Baghdadi in INRAE Montpellier. What's interesting when we want to look at the potential of such images for this application is to understand the current context and compare it to what existed 5, 10 years ago. Before, you had to pay for images, and the sensors had their revisiting time, which was limited. Usually, the sensor would repeat images in about 20 days, every 20 days, and the space resolution, the image precision was not was little adapted to agriculture because it was we dealt with large pixel, and mainly all the pre-processing of images were done by ourselves. Anything that had to do with collaboration and correction images had to be done by us. So we needed expertise in those domains, which is more physics of measurements, but we also needed a lot of tools for computation and computation power. Today, when I said today, I mean for about 10 years, data is free. When they're not free, there is favored access for researchers, and even the paying data can be obtained if we can justify the utilization for research purpose. What's interesting today is that the repetition time is more frequent, intervals are shorter, and images have a better resolution, and especially with the Cop- Copernicus European Copernicus constellation, and also images are pre-treated; they will be cleaned, and we can just move on to the application. All this fosters the development of operational approaches for mapping several variables: humidity, irrigation, land use, etc. Again, before going into the topic, it's interesting to say a few words about radar sensors and optic sensors. Radar sensors are all-weather sensors. We get data regardless of the weather condition. In addition, we use long waves, very high long waves. That is, we will analyze mainly the interaction with the environment. And it's been documented in the literature that radar signal is highly sensitive to soil moisture. So the radar signal will increase with soil moisture. Optic images are passive sensors who are penalized by the atmosphere, by the clouds mainly, but they're very interesting to see the chlorophyll activity in agricultural environment. And as I said early on, the Europeans with the Sentinel-1 and Sentinel-2 sensors, uh, and I said because the two sensors each time, they provide images with repetitivity intervals under the week, which is 10 meter by 10 meter, resolution, and it is well suited to the plot scale, and especially the European context when the 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 parcels are very large and the image interval is roughly one. We get at least one image a week. So all this is suited to the uh, so when we take about soil moisture, we got data which exist in the last few years. Some products do exist, and there are products coming from low resolution sensors, very low space resolution. You got a soil moisture map coming from SMAP. in the US. The second one is SMOS, which is a European sensor with a partnership with many other countries. But all this to say, the native resolution of the sensor is about 20 by 20 kilometers. And of course, the advantage of Sentinel-1 data, radar data, is to provide moisture map at a finer resolution at the plot level. So Copernican land already provide this. Copernicus land provide this, but provide map, but have only a 1 kilometer resolution. Now, let's go into the topic of the subject. What I said earlier on. So when the humidity of the ground increases, it increases the radar signal, and therefore, when we map irrigation, we'll try to detect. We see on the map two farm plots, agricultural plots, which is a good illustration of what I said. On February 13th, we had very humid conditions, lots of rain, and 13th of May, it was it had not rained for a while, so low humidity. When we look at the radar signal on the right-hand side with the color bar, what do we see? When we deal with a very humid soil, you have a very high signal, red, yellow. Right-hand side, when the plot is low humidity, we have a low signal with blue or cyan color. At the INRAE, we developed an algorithm called S2MP, which will derive soil moisture from Sentinel-1 and 2. It combines the radar signal and optic image to map humidity at the parcel, at the plot scale. This algorithm will model the radar signal by using physical model. It will use a model called the water cloud model and the integral equation model, because the radar signal will find on the radar signal images corresponds to the interaction of endemisms with the ground and with vegetation. So there is a mix between soil and vegetation. And to use optic data, we want to extract the vegetation component to keep only the soil component. And this soil component will be reversed to identify the moisture. And we use the techniques to do it. Algorithm has been validated, exists. The precision is about 6%. Degradation of estimation, well, when the NDVI is high, NDVI is high, well, it's only the wavelengths actually of the radar that I use. As I said earlier, we use Sentinel-1. It's the only one who are free and open access, but just data. Uh, and the problem is the vegetation is highly developed with high biomass. The signal, um, otherwise, and if it doesn't reach, we will have difficulty to assess the. So we will have to take into account the NDVI. So when we look at the maps that come out of this algorithm and try to analyze the occurrence in time, by comparing with the precipitation data provided by OR5 or on-ground stations, what do we see? On the map top, uh, we see in X the dates, and Y we see the soil moisture assessed, and the second axis in AREG is precipitation. So what do we see in dotted line? You see that soil humidity moisture will increase with precipitation, of course, that is with blue color. So the white chart corresponds to humidity. Each time there are precipitation increase, then it drops, and then rains, and so on and so forth. What do we see? Humid soil moisture assessed from satellite data follows the pattern of humidity indicated by the rains. If we look at the bottom figure, we see on the Occitanie region in the southeast of France, we see the moisture between color red and blue, and then we've included the rainfall. And then you can see that at that given date, the east part of the department experienced high rainfall, heavy rainfall unless the west when there is no rainfall. And if you look at the moisture map, east there is moisture with the blue-green zone, and on the west part, where there's been no precipitation at that date, we see moisture with the green or yellow color. So clearly there is a high coherence between assessed humidity or moisture and rainfall. Moisture maps exist already, done by l'INRAE in France and elsewhere, and data is free, available on the TEA website, French Land Center data. Data is available and can be retrieved by anyone who wishes to do so. Now, quickly, I'll go to irrigation. As I said early on, what's interesting with radar imaging, there is a high sensitivity of the signal, humidity, and irrigation. If there is irrigation, there is increase in humidity. In practice, it's more difficult to understand. Humidity may increase not because there is irrigation, but because of rain. So we want to separate what comes from the rain and what comes from irrigation. Yet, before going into what we do, it is important to know that water consumed is consumed in the agricultural by the agriculture, and with increase of population, there is an increase in for there is more demand for food, and therefore we increase agriculture, that irrigated agriculture, and irrigated agriculture consumes almost 40% of what is done for food production. Well, to see how we can map the irrigated surfaces, two illustration. First, top one, what do we see? In Y, left, the radar signal, what the radar sensors record. And this is done by the sensor in the surface. Second, the Y are the rainfall on the right, and X, well, the time. The three colors: blue, rainfall; green, radar signal for us, and then in red, we got the radar signal, which has been averaged for 10 by a 10-kilometer mesh. So when we look at the evolution of the signals at the plot scale, and what do we see in time, and the prairies, we see an increase of signal each time that there is a rainfall. We see it all the time. Green is highly correlated with red. And then what's interesting is that if you look at the black ellipse, what do we see? Well, a red signal which is stable, doesn't move because there is no rainfall, normal. However, the green signal, which for one irrigated plot, we see fluctuations which correspond to the increase of the signal because of higher moisture from irrigation. And we see some kind of repetitiveness of about a week. Plots are irrigated every week or 2 weeks. Everything you see in the ellipse in black, the fluctuations, all those fluctuations in the green signal, which correspond to the radar signal at the plot level, correspond to humidity fluctuation caused by irrigation. We know it is irrigation. If we look at the red signal on large mesh, we see the signal is fairly stable, simply because there's been no rain. There's been no rain during from June to August. Now, let's look at the second example on the irrigated prairie parcel. As I said early on, that is, if we look at the black, this is the radar signal at the plot parcel. In blue dot line, vertical irrigation data. Insight to knowledge of irrigation, what do we see? Each time that irrigation is done, signal increases. The signal increases because we can see the black curve. Then if we look at the big mesh, we see the red curve is stable in time because there's been no, between July and September, there's been no rainfall. each time when the radar signal increases at the level of the plot and it does not increase over large mesh size, it is caused by irrigation. So what do we do? Well, to map irrigation or irrigated plots, so there are several methods. Either we use supervised classifiers. We will collect data in a given catchment basin of a given year. We'll train, and then we will generalize the classification model by applying it to a large territory. Usually, these algorithms function over the same year or the same region, but rarely they usually they can be generalized. What we propose is a sort of a operational method of irrigation mapping by using radar and optic data, working on time series of data based on the agricultural cycle. The algorithm doesn't use terrain data, or we don't want to go, or whatever. So the algorithm will first, thanks to what I presented early on, the radar signal each time it increases, either it's the rain or it's irrigation. And if we can remove ambiguity caused by rain and saying this increase is probably caused by irrigation, uh, initially the algorithm will generate some kind of a reference database, irrigated, non-irrigated plots, when we know that when we certain it is irrigated or not, and then the reference database, as I said, which is generated by the algorithm, will be used afterwards to train another algorithm and then to run it over large territories or catchment basin. I'll spare this. This is exactly what I said early on. Roughly, we look at the diagram, top irrigated, non-irrigated plot, and bottom irrigated plot. If we look at the red signal and green signal don't move, they're not evolved, but the only times when they change it's because there's been irrigation. Bottom curve, it's an irrigated plot, and what do we see? The red curve is stable. The signal doesn't change, but the green, which corresponds to the plot scale signal, we got a periodical increase of the signal, which is a periodic increase of humidity caused by irrigation. We provide maps in France and in the world. Let me conclude with this slide. The irrigated surface algorithm works well if we are in a semi-arid area where or in a temperate climate with little rain in spring and summer, because it is done when there is a hydric stress, spring and summer. What we see here that in fact in 2019, here in this site, there was a better precision on irrigated areas than in 2017. 2019 was very dry summer, where 17 was a wet summer. Why are not we not as good as when it's humid? Because, well, we get to the limits of the system, we can separate the rain from the irrigation data. When there is frequent rain in spring and summer, it adds ambiguity and we are less precise. Now, if we look at the perform performance of the algorithm for irrigated surface air algorithm here mapping, we can see on the left the irrigation events not detected, non-detected irrigation events are high uh, when the moisture is high. So again, back to what I said. I said when there is high and DVI coefficient, that is the vegetation index, the radar signal doesn't go to the ground. If it doesn't go down to the ground, we don't know what happened there. So it is difficult to assess humidity, moisture, and to say there's been irrigation or not that day. So This is why the detection of irrigation events is good when the NDVI is limited or medium, but difficult when DVI is high because we cannot detect irrigation about 80% if NDVI is in excess of 0.8. So what are the limitations? Well, okay, it's all to say it works, but there are limitations. Let me summarize what I said. Results are not as good when we have rainy years. That is especially spring, summer, rainy spring, summer, simply because there is a confusion, despite everything you do, there is confusion between rain and irrigation. Why is there confusion? Because often in summer, even when it rains, there is irrigation. So then therefore it's difficult to separate the two because both cohabitate. Second point, for some crops and for certain growth rate for vegetation as well grown with biomass, the radar sometimes cannot go through the vegetation, doesn't reach the ground and the soil, and we cannot map the moisture. This second point is not an algorithm issue, it's a data issue. Today we work on Sentinel-1 data because they're free and the sensors have a wavelength of 6 centimeter. So when vegetation is well grown, we don't go there. Soon we'll have new sensors in L band, and such sensors have no problem to go through vegetation and we won't be limited. It is impossible to map zones with drop irrigation because we got humidity that will increase very locally in small surfaces. And today, the resolution of the sensors is not suited to this humidity variation. And the last point is that if irrigation takes place more than 3 days before, it is difficult to detect the irrigation episodes because, again, it is a prime of instruments simply because the current sensors have a 6-day interval scanned. Well, why not 3 days? Well, because when the plot is irrigated, well, humidity increase very strongly, and at spring, during the spring or summer, humidity, moisture will dry up rapidly within 3, 4 days, and after 5 days, of course, the soil moisture is at the level it was before irrigation. This is why usually when it's very hot after 2 days or maybe 3 days, humidity kept as the same order of magnitude of the soil humidity before irrigation. Thank you. Thank you. So you can ask question to Mr. Baghdadi on the chat. And so now, now we welcome Pierre Lemaire, research engineer, as we said, is specialized in imaging and geomorphology, river geomorphology. And a small detail for Pierre, do not hesitate to turn on your camera for the interpretation. It helps for the next speakers. Thank you. Yeah. Okay. Yeah. Okay. I will start. These are the works we've done to adapt AI. Well, we'll see what I will explain to the natural environments, and therefore the problematic was that of to characterize the grain size distribution of in rivers using aerial images. So what is the grain size distribution? We study the shape and the size of pebbles or pebble stones. If you look at the photos, they all concern rivers. What we can see all the photos are the pebbles. they have a it's a common denominator. Even when a river or a torrent or a mountain a river is dry, the stones indicate the life of the river. You know, this is added the size of the sediment deposit corresponds to the entrainment of strength of the river. So the position of the pebbles gives us an indication of the operation of the river. Why do we need this? Because pebbles will amplify damage if there is a flood. Their lack will amplify the incision problems, which may cause difficulties with infrastructures and especially bridges and especially resources. They will impact upstream from the dams. There will be an accumulation of sediment that will reduce the the capacity of the reservoir, and downstream the incision will cause damages, especially when it comes to the navigability, and the pebbles are part of the habitat of fish and invertebrates, so they have a biodiversity function. For all these reasons, it is useful and essential to measure the granulometry of such pebbles or stones. How do we do that? Well, clearly, we can go on site and sample pebbles, measure them using a gauge, or as you see on the right-hand side, you see a Wallman's gauge. And then we can also use sample pebbles, run them through mills or grids to measure the sizes. Two problem with such in situ measurements is that it is quite tedious, difficult, they're very intrusive. We need to sample pebbles. We have to move them, transport them, which may damage the environment. And these are, of course, random sampling. And we, of course, are submitted to variations and which call for operator expertise. You can't sample anywhere. There could be a lot of differences or problems depending on where the sampling is done. We want to measure the pebbles without touching them. That would be the role of teledetection, which is been developed recently thanks to drones, the use of drone, and especially what you call photogrammetry. Photogrammetry means that you go around with a drone around above a river and with pebbles, take photos, and you create a 3D model of a bank of pebbles, and we can have a what you call an ortho photo, auto rectified image, where each pixel actually is linked to a or geographical data or coordinate. The advantage is non-intrusive. It provides access and acquisition of a lot of information in very limited, in little time. However, there are drawbacks. One, which is we have only access phys, the the visible data, and we end up with data volume which are huge to be processed. Hence, uh, we don't want to take the photos and to go and click on all the pebbles to measure their axis A and B. So you see, for a few years now, we've developed software tools to automatize these measurements based on photos. I'll mention Base Grain, developed by the Zurich University. It is computer vision. It is parametric. In 2011, it was just before the neuronal networks, modern neuronal networks. So how does it work? Well, we look at the contrast locally, we'll extract shapes, and then we'll deduct the position of the pebbles or stone. The problem with such approach is that of all computer vision is that it is sensitive to the light conditions, and it is also sensitive to the very texture of the objects. And often we got cases where it doesn't work very well. Well, in fact, very badly. So a lot of action efforts have been made to understand and increase the reliability of such software. That was in 2011. Today, if we want to solve the problem, we will think about AI, an AI system. It's a bit of a rude word, AI. It can mean a lot of things, But let me clarify what I'm talking about this buzzword. Uh, I'll talk about neuronal networks with deep learning. I will not talk about I won't talk about model language, language model, sorry. So for a while now, neural networks exist since the 60s roughly, but there is a true acceleration since 2012 and a specific network called AlexNet, for example. So where can we set the boom? Well, 2012. Why? Because there is a massification of data, more data available, thanks to social networks. There is a booming of computation capabilities, especially with graphic processors and what some manufacturers do. And the diffusion of models and technique is really now has been accelerated through open source. Now, how do we apply it to detection of object? Let me the example of the mask RCNN, the model we used to pebbles. So we run it with supervised learning. We will provide it with a lot of images as examples with mask, which will show the what we expect from the network. We'll give a lot of example. It will take the same will take them, and they will learn based. It will learn based on probabilistic models to give us back the example provided. If we take an image like this one, it will explore all the possible zones in the image, and each time it will assess the likelihood of a presence of an object or not. And in zones where the presence is the highest, based on its prediction, it will it we will it will predict a class, a type of object, and it will give us the pixels which explains the decision. Now, the problem with such recent neuronal networks that we can see on the it is based on the daily life image, cars, dogs, bicycles, planes, people, cows. But in fact, it's not highly representative of the natural environments, and therefore it is such that even if we take a network that is very recent, high performance on the training sets usually utilized for detection, networks do not function well on our images. Therefore, here we got position with pebbles. So it detects snowballs, fruits. Uh, it detects a fruit salad with snowballs. So so why does it do that? Because in its learning game, it didn't have any example of data which is of interest to us. So we need to set up learning games or learning sets to tell them what we want. Therefore, we need to provide images of the pebbles already referenced. This is what we wanted to avoid initially, but the strategy we employed Galed V1, well, we generated a lots of synthesis pebbles. And the idea is that we detoured a lot of pebbles by hand. We did the hand cut. Then we generated other pebbles, artificial pebbles, which are we placed them randomly in in the styles, if you want, and we used a random background to give it examples of what is not a pebble and what should not be detected. Now, this network, we need a bit of engineering to deal with the orthophotos with this type of network. So it means that we will very much like a neuronal network takes only one set size image as an input. We will do iteration using basically, we by tile based. So we got assembling engineering, then the treatment of processing of characteristic. But we got a neural network which is now able to understand or perceive orthophotos with pebbles, which can make differences from fine granulometry from vegetation. And, and on these images, we see that we get indicators which correspond to the size of the objects. This network also makes it possible to understand the continuity of the shape of the pebbles, even when they're partly recovered or covered. It can actually restore their shape. So those are the works we did to train Galileo V1. It's mainly we set a learning data set, which is representative of our problem. This has been validated scientifically in several articles. Then we wanted to, we can call it directly from QGIS. So all people are also referenced. Then we can exploit the data, and then we put it in. It is available open source. I will give you the address later on in the chat, but we can scan the QR code to have access to the source code. It is, well, we're trying to document this installation to make it accessible. Now, we saw work done for the basis of a network which is quite old, which is dates back to 2016. And lots of progress have been achieved since. We wanted to upgrade it, so we subdivided the task in two parts. First, rotate, which comes up with boxes, which takes everything, which includes everything inside, and mobile SAM, which remove the mask to explain what we detected. We tried to train this system on the system of Galileo V1, but we had a problem with the realism of V1, of Galileo V1, and the more modern networks would learn to detect. Uh, then we had collage rather than detecting pebbles in natural images. So we had to redo a teacher-student game, and we used two strategies. We used first the strategy called the teacher-student, where we will show the images to a network, expert network, on the segmentation of objects. The idea is that we provide a point where we said this object, find the object that correspond to this point, and we can also provide it with negative points. We said this does not belong to the object. Then, and this network can also deal with a more general problem, with that of segmenting object in the broad meaning of the word, and therefore there is a good understanding of the images we show it. The problem, it will take all the objects, including vegetation, so we have to guide it for highly textured particulates. It takes a lot of resources, not applicable for a bench, and without retraining, it will only segment visible pixels. So we use it to provide examples to a learning network, which will be highly specialized in our data. So this is an example of the learning game using segment and think. And from that, we were able to make a lot of annotations, but was not sufficient. We needed more. So we went to a synthesis strategy. And for this, we used the generative models, which would generate an image based on text, on prompts. And we used stable diffusion. Stable diffusion, for one reason, is that we can add a network which is called control net, and which will guide it in the generation. Here you see we asked it to generate pebbles on the sand background following the contours, the silhouettes that we created with the same strategy as for Gallet V1. So we get the photorealistic images and we know the position of the object, and we pushed it even further by asking it to apply a style using a menu called roof. And the idea is like if we asked, we show it examples of a Rembrandt painting, and we ask it to generate pebble images and the Rembrandt style. And usually those would be pebble imaging as a drawn style using a couple of examples. So results is that we get photorealistic images almost fully annotated, which could mislead. Now, let me show you the results. We compared the performance of Gallet V1 and V2 versus other competitive systems which do the same thing using a limited set of data of images from riverbeds with pebbles. We're quite happy actually because globally we got more detection with Gallet V2 and with little false positive, very few obvious false positive, which was confirmed by a study which we produced. And the other reasons for us to be happy is that we realized that the Gallet V1 is still doing well, and the two versions produce a lot of mask in little time versus competitive network. And let me show you a couple of applications. Within the framework of a study, we did photogrammetry of the Lulion, which is a tributary of a river in the Maritime Alps. At the bottom of the image, you see two tiles where we run the teledetection. Here you can see all the remote thing. You see all the sensing at a larger scale. Each dot, each mask corresponds to a detection, which were colored based on the size of the objects, and we are able to come up to a scale uh, of several kilometers and to aggregate data, and especially giving a conventional granulometry indicator D84, and therefore we can get the more exhaustive data and specialized indicators, and more what we'll see where we would have a linear of a few hundred meters along the river. Let me show you another example on the Breche uh, bench bank of pebbles on the Breche. You see zones, and when we run the detection, we see that the sensor, without being trained specifically, can actually detect the pebbles which are immersed or outside of the water or emerge. This was not possible with Woolman on site. And then when we look on the right-hand side of the image, you can see shapes. You see the orthophoto. We can see some shapes, and thanks to remote sensing with visualization, simple visualization, we can find the pos the previous positions of the bench during the previous floods. Likewise, this is a new data to which we have access thanks to AI. I know I'm running out of time. Let me conclude. Lots of things remain to be done. Let's hope that there will be better adapted networks to the natural environment, but we need to find strategies to adapt the networks and to the AI in general to our data. And then there we have to ensure the reliability of the results. Networks are often higher performance in some case, not so good in others, and we cannot explain why truly. So we need to consider networks have new sensors. Sometimes they're very noisy. They have a lot of background noise, and we have to study cases where they don't work well to to reproduce data, training data, to retrain them again, and so they will behave better. In such by the way, let me remind you that you can test Gallet V1, uh, Gallet V1, which is an open source. Thank you. Thank you for this presentation, and especially thank you for explaining the limits and the problems. Now let's move on to the third and last presentation. Okay, thank you. We will now listen to Mrs. Schymanski, and you'll talk about water contamination and your environmental chemio computer techniques. Thank you.
Thank you very much for this opportunity. I'm going to talk to you today about exploring water contamination with open cheminformatics approaches. Because I tend to speak rather fast and I will show a lot of different tools today, I've also made my slides available on Zenodo. You can download them at this DOI here or just use the QR code in case I speak too fast and you miss something. So what is environmental cheminformatics? I mean, in very basic terms, we take a look at the environment, we get different samples, we then query this environment with high resolution mass spectrometry, and then process this data. This is where the cheminformatics comes in, with the eventual aim to identify chemicals and their toxic effects. And what sounds relatively simple, I will try to show in the next slides, can be a little bit complicated. As a group, we also develop a lot of different software to do this, and I will run you through some of these developments and then how we can apply them today. Also bearing in mind, we don't have terribly much time. Our biggest challenge is our vast chemical space. So as you can see on the picture here, our chemical knowledge is kind of like space right now. We have a lot of it documented. We have 119 million chemicals in one of our largest open databases. But what we know is this is not everything. We can't even enumerate everything. So just like in space, we have an unlimited space and only parts of it within our reach. And if we're thinking also in the terms of AI and needing this known data to get good predictions, we basically have fingerprints, the mass spectral data of less than 0.01% of even this known knowledge. So one of the biggest challenges in chemistry we have is there's actually very little of the chemical space that we're dealing with that's documented in the level of detail that we'll need. As analysts, we interrogate this in a large number of ways. So we can have what we call target analysis. We know what the chemical is. We have it in our laboratory. We measure this, we look for it, we quantify. We can also do what we call suspect screening, like say, for instance, we're interested in the pharmaceuticals that are in Luxembourg. We can go to our health service, download the list of pharmaceuticals, look for them and see which of those pharmaceuticals do we see in the water. This is what we call suspect screening. And I'll introduce in a few slides the Norman Suspect List Exchange. This is our way of gathering the expert knowledge together. In total, we have 131,000 chemicals now, but a suspect list is meant to be a little bit smaller than that, so you can do a small view at what's in your sample. And then we have what's called non-target screening. This is our way of looking at the space, knowing that our instruments can't see the entirety of space at the one time. We have to make some compromises there. And we also develop databases so that we're not screening the entire 119 million of PubChem, which is huge, but that we're screening subsets that are relevant. And this is also where things like AI can help in the future with interpretation, relevance, what do we screen, what won't we see, all these kinds of decisions. So gathering expert knowledge is one of our biggest challenges. There's a lot of really detailed knowledge in relatively few people's heads. How can we then capture this knowledge and exchange it in a resource that people can find? And this is one role that the Norman Suspect List Exchange has. We're redesigning the website as it goes. So if you go to the website, it looks a bit boring. It's just a table with lists of chemicals. But just to hammer at home how many experts are out there and how much knowledge we need to gather, this was the publication we released in 22. We had 97 authors on this publication. We just missed the 100 mark, but that shows how many people actually are contributing to this knowledge base. And the way that it works is that we take this diverse set of suspect lists, so we don't mandate the format so that we can actually capture a wide range of different inputs, also detailed environmental reports, all the way through to experts that know how to provide us with a verified list that we can pass straight away. We then put these on the suspect list exchange. We put them on Zenodo. And through Zenodo, we actually get download statistics. So we found out while we were compiling the paper that our cosmetics list was by far the most popular list out of our entire 100 lists. And then what we also do is we put them into the central Norman Sustat, which then feeds the other database modules in the Norman system. What we also do is feed these suspect lists to larger international resources that have larger audiences than we do. For instance, the CopTox Chemical Dashboard from the US EPA and also the PubChem database, so that our knowledge isn't just restrained to us, but also accessible in other databases as well. And so one perspective, I mean, it's actually happening right now, but where we're hoping to go, and with the help of AI, we're hopefully going to get there faster, is these resources such as the digital sample freezing platform. Here we have a little drop-down menu where you can select the chemicals, and then you can actually look at a map of Europe and see where are there concerning concentrations or intensities of this chemical in the different areas. And what we're basically working on now is turning this into a future early warning system where, with AI and the help of efficient algorithms, we can actually make this computation faster, more intelligent, and also come to the conclusions a lot quicker. I already mentioned mass bank. I mean, part of our huge challenge is getting enough data. So we also maintain this spectral library where people can submit their measured spectra of the different compounds. And here I'm showing an example from Luxembourg. This was Anjana when she was still a master's student in our lab. She did the first Luxembourg contributions to MassBank. She's now actually working, or she's managing the PubChem integration of MassBank, so that, again, it's more accessible. And a lot of these experimental spectra are actually the data sets that are feeding a lot of the machine learning developments that we're seeing in silico fragmentation prediction of mass spectra. We also work on this PubChem Lite for exposomics. So this is, I introduced it very briefly before. This is how we look at the chemical space and subset it according to the chemical classes that are relevant for at least our experimental contexts. I won't go to it in too much detail, but I'll just show some of the visualizations and their relationship to AI. One thing we can do is just a very trivial star plot, but this also shows what categories of information are available for different compounds. I will get back to these literature and patent stripes later, because these really show the time trend of information that we have on the chemical. And the other thing I want to highlight is these collision cross-section values. I don't have time to go into the technical details, but this is basically, in a complementary way to the mass spectra, we can get the ion mobility spectrometry or spectroscopy that is basically capturing the cross-section of the molecule. And from that, we can actually determine different isomers even when they have the same mass. And what's cool is these days we have now enough experimental data that we can actually get seriously good machine learning values. They're not quite as accurate as the ab initio calculations, but we can run them in seconds to minutes rather than months on high performance computing, also for a much larger domain of chemicals. And this basically means with PubChem Lite, we run a version of this every month, and we actually have the values available, updated for the updated collection within minutes to hours. And this means that we can then do reproducible calculations much quicker. It also means when we get new data in, they can retrain their model, improve the predictions, and we can update our resource in a feasible time frame. So high resolution mass spectrometry, it's not just about the measuring and the data processing, it's all about setting up the experiments as well, the experimental design, the analysis. We can do a lot of archiving, but you can already see from this picture, there's a lot of room for algorithmic improvements in here. What do we actually do with this? Well, one of them is to detect unknown chemicals due to standout patterns. So this is an example from the Rhine River. And you can see here at the top, we've got one chemical that pretty much only appears in the river once a year. But when it gets above this level, the Rhine is a highly diluted system. So if we see it above the intensity threshold we're concerned about, this actually means 0.6 tons of that chemical is going through the river, which is actually quite a lot. So we have this automated triggering system, and when something sticks out like that, you will then go back and find out where is this chemical come from. At the bottom, you see we had kind of the opposite case. We have a signal that's happening all the time, and then all of a sudden it would drop out for a few weeks and come back again and then drop out again. And this was a signal for a production break in a factory. And what happened when they figured out where this was coming from in 2014, they were actually able to trace it back, go to the company that was able to put in a mitigation measure and basically reduce the concentration of this compound. It's not completely eliminated, but it's a lot less of this compound is now coming into the Rhine River. And we can take this one step further. This was just two examples, but this is an example from Vittorio, who completely coincidentally emailed me yesterday out of the blue. And he was actually grouping these chemicals, what you can see in the colored lines as chemicals he could identify with the other chemical signals that we see, but we can't necessarily identify. In this way, you can actually group them and see if you can act on some of these chemicals according to the groups of the signals. We also have a couple of maybe simpler examples. We have looking at the pharmaceuticals that I mentioned before. You can see we have a very systematic trend. 2019 in purple, much higher concentrations. 2020, we actually had a dropout of most signals. And in Luxembourg, we have a lot of cross-border workers. So when they were in home office, we actually had a lot lower human signature coming through the wastewater in Luxembourg. Interesting thing was a chemical like nicotine. This really is heavily driven by the population. And you can see this almost halved. And then we had compounds like iohexol that actually disappeared completely in 2020. This is a contrast media for cancer diagnosis. And of course, the hospitals were full of COVID patients and they weren't actually doing any diagnosis. We also have pesticides, and this is highly relevant for improved prediction because this is just a manual example, but pesticides don't just stay constant in our environment, they transform. And what we can do with various predictions, you can predict what transformation products we're going to get. We can also predict what retention times they're going to get. So then we can look at the data and see, does the structural prediction match with the property prediction? Does it match with our observations? And if the screen is not too small, you'll see that the top one and the bottom one both occurred at the same month. So they're in green, they're both occurring in July. And the middle two, although they would match in terms of the retention time shift, they actually occurred in a completely different month. So they're probably associated with a different chemical. And again, this transformation product prediction, this is highly combinatorial expansion, or very, it suffers a lot from combinatorial explosion. And so one thing we've done is actually, how do we get more data into the databases so that we can improve the predictions? And actually, when we submitted this paper, the reviewers got back to us and said, oh, you should be using AI to do this curation. And our argument was, well, no, we don't have actually enough curated knowledge to get the good predictions to be able to get AI to help us with this curation yet. But what we did is you can do a name recognition, and this data actually came from PubChem. They did the name to structure mapping. And then what you can see is that some of these are very obviously true positives. The match makes sense. Some of them were just a semi-match, so the triphosphate instead of the acyclovir triphosphate. And some of them were clear. The name was mentioned, but it has nothing to do with the transformation reaction. So one of my students actually worked up a little app so that we could automatically read in this data and enable this curation so that we can actually add more data to the data sets to improve the prediction. We're actually working with the biotransformer developers on this. And through this, we've actually been able to add thousands more reactions and also start to recognize which reactions do we see, which reactions don't we see, and can use this to help constrain the predictions. Where do we want to go with all of this? I mean, in an ideal world, we would look at our sample, do a combination of suspect and non-target screening, do a first pass on this, have a look at what the signals are, then go into the databases, retrieve the known transformation knowledge, use this to kind of build another library that we can screen in the samples. And then through this, you can actually start to build the story of the relationships of the peaks in our sample and start to bring together knowledge and not just random hits. And of course, as a second step, what we have is the predictions as well, that if you can't annotate transformation products on the known knowledge, we can also do the predictions and look for them. But instead of getting a few matches, you quite often end up with dozens to hundreds of potential matches. So it's computationally much more inefficient. What we're dealing with is a huge influx of chemical information. So I don't have time to go through this graph in detail, but I'll just run you through this axis here. You can see this exponential growth. And in a way, I hate exponential growth as a term because it's so overused, but this is really what we're seeing. And what's more, this is not the growth in the number of chemicals overall. This is the exponential growth of the number added per year. So this is actually up to a level of 20 million chemicals being added per year to the databases. And as you can see, also the information available about these chemicals is increasing. So the red shows a higher amount of information. So assessing these chemicals coming in at such a rate is extremely difficult. I showed a little bit about the trends, and actually, although we see the vast majority of trends look exactly the same, if you color it the green to red, of course, you can always see it green, a little bit of yellow, and then going to red. And we were like, okay, it's always the same pattern. And lesson number one, when you're doing computational methods, always test random numbers. I put in 1, 2, 3, 4 because it's a cool number, and we suddenly got a completely different pattern out. And it turns out when you do the reading that this compound was a pharmaceutical that was highly promising in clinical trials. So it went through actually to clinical trial, had very severe side effects, and was actually taken off trials and any further tests after that. So this spike really made sense. It had a lot of attention and then dropped down again. And we actually started reconciling this with real examples that we were seeing from our colleagues. So this is Daniel Sahn, who was showing images of compounds he's very concerned about. He's already seeing in the wastewater that they're struggling to remove when they do wastewater treatment. And we were at the conference with our chemical stripe generator, and we basically did a live stripe, and we saw for the one he mentioned, we didn't see anything abnormal with the pattern, but then for one of the related products, lithium tetrafluoroborate, this was the only chemical for which we could actually get a stripe where there was orange at the end and not green, because we have a little bit of a data lag. And this is a substance that is associated with electrical vehicle production, and the patents for this is obviously going through the roof at the moment. So this all started to make sense. Without boring you to death on all the detail, we actually did a deeper trend analysis in these patent data to see, can we really start to see which chemicals are trending in different regions or in different areas and subjects to see if we can catch the new and up and coming contaminants before they become a problem. Why is this relevant? I don't know how many of you have seen the discussion about the forever chemicals, the polluants éternels. I'm sorry, my French is terrible, or the Ewigkeitschemikalien here in Luxembourg. There's a lot of debate right now about TFA, and they updated the definition of a PFAS to anything containing a CF2 group that was saturated. And when we mapped up this new definition with a database the size of PubChem, all of a sudden we're not dealing with the tens of thousands of PFAS that they're talking about. We're dealing with 7 million of them. And again, we have documented production of TFA from a teeny tiny portion of this, a few chemicals. So again, how many of these chemicals are actually potentially going to produce TFA? How many of them are actually a concern for us? How many of them are used in amounts to be concerning? So we started looking at property prediction, and even if you narrow down these queries to get much smaller numbers than this, we were querying a few different substructures that we're concerned about. And unfortunately, what we can see from a large numbers of chemicals, even if we constrain them, most of them fulfill potential mobility by predictive methods, and most of them are predicted to be non-biodegradable, which means that they're basically, from a persistency and a mobility point of view, of concern. The lower bar that you see here, this was using one of the state-of-the-art softwares in environmental analysis. A lot of the contaminants were outside the domain, which again gets back to the lack of data. And it was somewhat difficult for poor Emma to calculate this on the machines that she was using. So again, this is one way we hope AI and machine learning methods read across over time will improve, like we have already got for the collision cross-section values. Those numbers seem really scary. So the vast majority of chemicals seem to fulfill the criteria for PM, which means there would be environmental concern. So one way of bringing this back to the reality that we see is, okay, what do we also see in the environment? So we don't panic about the millions of chemicals, but we can also use known knowledge in combination with predictive knowledge to say, okay, these are the ones we really need to focus on the most and invest our effort here. So sorry for going a little bit over time. I get very excited talking about chemistry. I'd like to thank you for the opportunity to be here. I hope you all understood what I said well enough. And thank you very much. I'm happy to take questions. And again, my slides are available on this QR code.
Thank you. Interesting presentation, good illustration. So now let's move on to the Q&A session. You can address questions to all speakers or one or the other, for those who understood it, that is. So, and speakers, feel free to answer if you want to or not. So let's move on to the questions now. We have a question to Nicolas. To meet the needs you expressed, how long does it take you to provide the maps in general, the mapping in general? How long does it take you? Well, it will depend mainly on the zone studied. If the study zone is 100 kilometers by 100 kilometers, 5 kilometers by 5 kilometers, today with the computation means it takes about 3 weeks. It would take me about 3 weeks. How do you design AI in this domain? Do you have people who are specialized to AI, others for interpretation, or is it, how does it work? How do you share the work? Well, in fact, initially, it is a signal processing work, analyzing the information. You cannot do AI if you don't understand what goes on. The most of the work, the most important part in this work is to analyze the signal and understand what goes on. And then once we understood that, we'll deploy, use a method based on AI. It's today, everybody do, IT, neural network, and so on and so forth. But the AI part is more um, we want to develop what we observed and what we understood by analyzing the signals. But I would say the most important part is not the AI. The most important part is what goes on upstream. What's the data that is useful to map irrigation? What are the limitations and how can it's the algorithm part. Once we got that, IT will follow, it's just methods, approaches. Some are doing well, others not. I mean, but it's basically it comes at the end. This question is also good for Pierre. And Emma, possibly Pierre Lemaire, but possibly Emma. In your structures, how do you work with AI? Well, in our structure, we have two engineers who will be specialized in the training of models and the exploitation of models, how to program modules that will use existing networks. And no, sorry, no, two, no, three, in fact, because we also have a PhD student who started his thesis on this topic. We don't necessarily modify the topology of networks. We'll find ways to train them again. That system that will work well, function well for the context. And then after that, the rest of the structure will exploit the results we provide. Emma?
Yeah, we use a lot of resources that have been built using AI and machine learning. We're getting into developing things ourselves, but we haven't done this extensively because our specialization as a group has also been providing the curated content that others can then use to develop the methods. So, like I said, with chemistry, this has been really difficult because the amount of knowledge we have about chemistry is relatively limited compared to the space we have. So we've been trying to cover the other parts of space that is not yet documented, working with those who are developing the methods to test them out and test out the limits and see how we can then apply this to our case studies. So I don't know if that answers the question, but I know from the chemistry point of view, we have a lot of different, if you set up efficient models, you would use a 2D structure. There's also been a lot of debate how you give the models the format of the chemical structures, and the results change a lot based on this. A lot of the data is also mixed in different forms of the chemicals, which means at an abstracted level, the predictions are not using sufficient of the structure to actually get the right results. So we can kind of see you asymptoted to a certain level and would need to actually go back and put another layer of complexity on before we can actually get the correct conclusions that we would expect. So it's super interesting.
Thank you for your cross views. Last questions to Mr. Baghdadi. You said that for the drop irrigation, it's difficult to detect this irrigation. Now, if you imagine a change of practice in terms of water management, how could we test the efficacy of AI with the models you use now on this new practice to make sure that it can be employed and how to develop new models? It's a complicated question. It's a complete question. That is, if we, the main problem is not AI issue, it's a data issue. If we got satellite data and the pixel is on average 10 by 10 meter, or even 5 meter, roughly, and that within this 10-meter pixel, we got about 5% of the surface, which has been modified through water contribution or irrigation, the average signal on this pixel will contain very little information about the irrigated zone. Now, of course, if we are dealing with probes or sensors which are airborne, drones or like that, well, we are dealing with a space resolution which are much finer, and then we can be more adapted to this type of application. So if we are more in on drones, we could hope to, well, to detect this modification of moisture where it is done, and then of course once we have the instrument that makes it possible to detect something, well then AI will come. So what I mean is that never forget that AI undergoes a lot of development. It's great, but for AI to be great and you need observation data. If you don't have observation data, if you don't have data collection, your AI is useless because the traditional method for are quite sufficient. The usual today, AI you can put out, you can adapt it. It's kind of a global trend, but we can see that for many applications, AI today does not provide something quite exceptional versus the other method because simply the data, observation data, in situ data, which is the most important, in fact, and very little is said about them, are not large enough today in quantity to do smart training and or learning and to enable performing system to have a better operation. That's why AI is important, but do not forget that the most important part for good AI to function, you need data and you need the understanding of the phenomena. It's only with that that afterward we can move on to the second phase, which would be the elaboration of a more sophisticated approaches. And of course, AI has lots of neurons and lots of heads. Great, great. But if you can't get the sufficient training upstream or good understanding upstream, it's useless. Uh, you don't do better than the conventional methods. Thank you for your answer. So again, you will have the opportunity to discuss that, to see this in your questions. So Pierre Lemaire, there is a question here. How this black box, you said that you work with algorithm developed by other individuals. How do you manage the when the fact that you don't know what is you don't know 100% of the algorithm, or how do you work out this? And well, we work a lot with networks which are open source, shared. So how do we work? What how the tool is made, the algorithm is made? Well, you know what happens. Well, we can understand. We know it's easy to understand concretely. However, the problem is that these are networks with depths which are huge, trained on huge data volumes. So how has it been the way it has been parameterized itself, or there are leads to the explicability of neural networks here with text, very much like what ChatGPT does. ChatGPT, by the way, it's a network that will just find the most likely combination continuation of words to be credible, but he has no reasoning. All it has is huge amount of data to learn how to respond in a credible way. But in all cases, these are networks that will, well, to go to the to understand networks today, we are working on we consider the network as it generates its output, it explains with a phrase why it did it. These are leads to explain the behavior, but still, in all cases, there will be a lot of weight to for neurons which have been trained, and this we can't control. Information is too complex to understand it. This is why there are black boxes. And I don't quite remember the question actually, says he. So, well, this first part, of course, I didn't know that, but it's interesting. Now, how do you, well, when there is the black box effect, what could be the impact for you? Well, in fact, we have to envisage a maximum number of cases in our test and our learning data to minimize the the out the network output, which could be completely off track. So when the network doesn't have an expected behavior, it's because it didn't get the right data in. So we have to pay a lot of attention to the model, the predictive model, in the case of global warming or others, because we're going to unknowns. And when we enter data space that networks have not seen, we cannot predict their behavior. So how can we develop the learning data that will the most representative of our problem and that will have as little bias as possible? This is on the design of the learning game and of the learning strategy that it takes place. Thank you. Thank you for your answer. So we do have another question concerning the positioning of the pebbles. So the AI identified the pebbles and is able to calculate the the grain size distribution, the shapes. Did you see the error rate for two pebbles are overlapping? For example, the AI can imagine the shape of the one below it, but are there error margin rates that you have identified or not? How does it happen? How does it take place? Sorry. Well, that's the problem of well, of the measurement of performance. To measure the performance, you need an objective data and the performance indicators metrics, which means that we need annotated data. And since we got a lot of objects over huge surface areas, it does not, there is not a fully annotated or human verified data on the banks of pebbles, and this is what we're doing. We're extracting indicators uh, by comparing it to measures done directly on site by measuring the pebbles, and we compare these land this reality from the site with the output of the algorithm, and we'll see what is the error margin, limited error margin. Today, this is the way we function and the way we check the performance of the algorithm. Otherwise, we can, we could, we can compare it to the test data put aside during the training period, but this is the way we measure the performance. Thank you. Thank you very much for your answer. We move on to questions to Emma. How could you improve your algorithm and what do you do to achieve that?
That's a great question. So, well, we have a lot of different pieces of the puzzle. One of the areas we'd really love to have improved would be actually the toxicity prediction. I think so for our community, this is the most important way that we could then determine the chemicals that are really going to be problematic from those that we maybe don't need to work on so rapidly. What we've done a lot of work on is, indeed, I didn't have enough time to explain it in great detail, but breaking chemical space down to the chemicals that are most likely to be found. So at least we can come up with interpretation and decisions rather than what we saw. A lot of people were wasting time on chemicals for which we didn't have enough information. We could never confirm them, and everyone was kind of stuck. So we're kind of moving from this era of just trying to identify to trying to interpret. On the one hand, we need greater efficiency to be able to run the calculations quicker. We still, as we've had in these discussions, we still need more data. So for now, it's really easy to get funding to do cool algorithms and new interfaces, but it's really hard to get funding to actually acquire new data. So either experimentally or to just get money to curate the data. So honestly, almost all of those of us who work on algorithms say the best way to improve them would be more data. So you can get maybe, I think one of the other speakers said this as well, you could maybe improve with a slightly different AI algorithm or approach, but the improvement would be so minimal compared with if you would have double the data, you would possibly still get a much better improvement even with a lesser method. So did that answer your question?
Yep. Yep. Thank you. Second question. You talked about the creation of new chemical compounds and the pollutants. Two questions in one. For this, do you use a predictive algorithm based on data acquisition or on the calculations and equation that you create? And second question, using these detection methods, could you consider detecting zones where chemicals could be accumulated and processed or controlled?
Yes. So this is part of the bigger picture. I mean, if you imagine the picture I showed with where the chemicals are occurring, this is exactly what you're trying to do. Where do we have hotspots that we could treat relatively easily? You have some contamination. We also saw the trends, which ones actually follow a certain trend, so you can really trace them back to the source and understand where it's coming from and act. Other ones, it's such a diffuse picture, we're not really sure where the chemicals are coming from. In terms of our algorithms, I showed it on the one slide. What we try to do is use a combination of knowledge-driven and also predictive methods. And a lot of people are trying to move just to predictive methods, but I think I've found it really interesting to hear from the other fields that sometimes the traditional knowledge-based driven things also give us good conclusions because we see the same thing. And we evaluated, even just taking fragmentation prediction as an example, we evaluated the different models state of the art in 2016. And what you see is rule-based knowledge versus the machine learning ones at the time. And of course, they've improved since then. You cover complementary space. So actually, the combination of all of these methods always gives you better results than just one or just the other, still. Maybe at some point we'll end up in an era where the predictions are good. What we've also found with the collision cross-section, for instance, is applying these predicted values, the machine learning predicted values, to real data and seeing where they help and where they don't. This has actually really helped us identify the data gaps to go, okay, for PFAS, we were not getting good predictions. And there's actually one researcher who's picked up on that, and she's providing detailed PFAS data to expand the chemical space and improve the calculations that way. So this is also the way that as a community, we can, when we share the data, when we look at the data in real use cases, we can also see where the gaps are, improve them, and then, gradually build this picture. So it's actually been a fascinating field to work on.
Last question to all speakers. The non-AI specialists, and especially when you consider ChatGPT, people think it's easy. But what we understand from your presentation is that it calls for huge of the work in development. Do you think for the general public, public should be made aware of the fact that you need lots of preparation and Open question to the three speakers. Shoot. Well, obviously, yes, of course. You have to raise the awareness of the general public. As I said today, often there is a poor understanding. Well, the word artificial intelligence is misleading because usually by intelligence we mean reasoning. And today, in fact, neural networks, it's purely the perception. That is, they are not able to reason. And they have a very abstract representation of data, but not of the world. There is no. They don't have a deontology. They don't have an ontology. So they could not copy the reasoning, ontologic reasoning. So the perception is misleading there. I think that we need to educate the public at large in this, the general public. I want to say something else, but I agree with what you said by Pierre. What is clear is that AI is one of tomorrow's scientific tool, but you need data and a good understanding of phenomena. What is deplorable today? We see a lot of publications, from the Chinese, but others. But a lot of publications, articles, people take data, they launch AI elaborated method, they get great results, but it's not because it's extraordinary, it's because the model is so well set and calibrated. But when you look at the physics behind, it's nothing's physical. People today use AI or highly elaborated IT methods to come up with a result, but there is no interpretation. And often I would say physics is wrong behind it. The underlying physics is wrong, but people will look at correlation, looks good, all great, because they use very few data. That's all. So AI is interesting, but you have to be very cautious because if you don't try to understand the phenomenon, if you don't do physics behind it, there is a second point. Well, about 20 years ago, when we did neural networks, we did a code. We had a code with 50, 100 lines. Today, when you do neural networks, you get a black box with 3 code lines, and that's it. Great. But for AI, it's roughly the same. It will be even faster. Some people will do development, great. Some people are very good for that. And then a lot of people will use things which have been well developed because all this will be prototyped in boxes, and that's it. So if you're not very good in IT, it's not lost because good IT people will develop things, and we are physicians or chemists or whatever, and we'll use tools which are sufficiently elaborated to understand the phenomenon. So work for everybody. So don't worry if you're not good in IT because it's not very. If some people will work on that, they will do good prototypes, and the true science today, true science for us for work on the environment, it's again physical phenomenon. Why do we see them? What happens? What goes on? Emma, contribution on this?
Yeah, I just give a very brief one. I mean, we've all seen what's happened with the search consoles now. So if you go to Google and type in a question, you'll get the answer back. And I've still had countless ones where you've put in the question and it will give you, no, 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 this doesn't happen. And then right underneath, you will see all the pictures showing exactly this thing happening. So, and I think also over time, people will begin to see that the algorithm sometimes gives wrong answers because it pulled it from one resource and, they reference it now and the answer was correct in that resource, but there's evidence right under it to show completely the opposite answer. And we've experienced the same. We actually worked with actually a French colleague. He's in Côte d'Azur. He spun up a chatbot built on scientific papers, and then you could basically ask it questions. Oh, can I analyze this using LC? And you would see sometimes go, no, 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 this one's only with GC, which would, for the chemical I asked, be the correct answer. And the next time it's saying, yes, you could measure that with LC. You just have to test this and this and this, and it would basically give you the protocol of how to try it. Even though, like any expert would just look at the structure and go, no way would this ever work on LC. So I agree with the other comments. It's basically, it's just starting. We know a lot of developments are going to happen. We can see that it's going to be powerful, but if it's just reproducing knowledge in a mixed way, sometimes the right answers are coming, sometimes they're not. I've already reviewed a paper that must almost certainly have been compiled with AI because it read beautifully. It was a fantastic piece of work. And for an expert, it was totally meaningless. One reviewer loved it, two reviewers hated it because it didn't make sense to us. And that reviewer that loved it probably thought it was a well-written paper and he learnt a lot because they weren't, or he, she, they weren't familiar with the material. Anyone familiar with the material's like, okay, you've sorted it out, but the way you've sorted it out doesn't make sense. And that gets exactly back to what Pierre was saying with the ontologies. It sorts out things in a random way that doesn't necessarily reflect how we would do it. So it's just the beginning. It's exciting. It's difficult, I think, as scientists also to have to see this. And at some point you start to see responses coming that seem to make sense and you start to question yourself as well, what is actually right? And I think this is also one of the very big dangers. When do we start believing the machines instead of believing the experts? And when does this boundary blur? This is going to be very, very difficult.
Thank you for the answers. So we're running late. So I have one last question before giving the floor to my colleagues for the conclusion. A question to Emma. As a researcher in another country, how do you see AI and how do you get support in the development of AI and how?
Yes, very much so. It's a big focus here. So, I mean, Luxembourg is a relatively rich country as well, so they're very much investing in these fields and high performance computing, security, fintech, also for the biomedical point of view. So yes, there's an incredible amount of investment in AI at the moment, but I think this applies also to many locations. We also have a lot of people. I mean, this is one of the major jobs that we'll have in Luxembourg. So as an institution, these are one thing we're having to build up, and we're also, what we noticed in our data science students this year, this is the comment from the teacher who actually directed the course, is that all the students now gave effectively the ChatGPT answers, but didn't learn beyond that. So we designed the questions in a way that you would know if you got the ChatGPT answer, and then if they'd learned the step beyond, you would have got a little bit more out of the answer. So I think one of our struggles as an institution is how to educate people how to use this and then how to still do the thinking and exactly have this critical feedback. And I know this is deviating from the question a bit, but this is, I think, what we as teachers are also faced with, having the time to basically adjust to this very fast moving field, integrate it into your research, integrate it into your funding proposals, integrate it into your teaching, make sure that people learn. While this is all, I have the feeling, changing almost daily. So yeah, it'll keep us busy. I think that was a good question. Never fear, we will still have jobs.
Thank you for connecting. Thank you to the speakers.